Hello everyone. Today we are going to study fourth chapter, Properties of Matter. And today's topic is elasticity. Today's learning topics are elasticity, stress, strain, Hooke's law, Young's modulus, and work done during longitudinal strain. So let us see elasticity. We know that physical properties of matter can be observed and tested. They include properties such as color, length, volume, density, and odor. Along with them, viscosity, surface tension, and elasticity are the major properties. Generally, all bodies have a certain change in their physical dimensions under applied forces and have a tendency to return to their original state after the removal of deforming forces. Means elasticity is the tendency of a body by the virtue of which it opposes a change in its shape and size and regains its original dimensions as soon as the deforming force is removed. Deforming force is a force such that it changes the shape and size of a body. So the force is called as the deforming force. The bodies which can recover their original state completely and immediately after the removal of deforming forces are called elastic bodies. Means there are two types of bodies, elastic bodies and plastic bodies. The example of elastic bodies is rubber, a quartz fiber, etc. And the bodies which cannot recover their original state are called plastic bodies. Its example is lead or plastic. Means there is a permanent deformation in case of plastic bodies, and in case of elastic bodies there is a temporary deformation. Then stress. When a force acts on a body so as to change its shape and size, then internal resistive force is developed. So long as external force is greater than the internal resistive force, the body undergoes a change in size or shape. If internal forces are equal to the applied forces, the body will not show any change in size or shape. For example, when a wire is elongated, then internal forces increase until it is equal to the applied force. So, stress is the internal resistive force per unit area of the body. This is equal to the applied force per unit area. Means stress is also a ratio of force per unit area. Mathematically, stress is equal to force upon area, or stress is equal to F upon A, where F is a force applied to a body of area A, then stress is equal to F upon A. SI unit of stress is Newton per meter square and CGS unit is dyne per centimeter square, and dimensions are M1 L0 T minus 2. Then second parameter is strain. We know that when a body is subjected to an additional force, there is increase of stress. When a body is acted upon by a deforming force, it undergoes a change in its shape or size. The change in dimensions per unit original dimension of a given body when acted upon by forces is called strain. It is a ratio of change in dimension to the original dimension. Means if we consider a wire and some force is applied to the wire, then it get elongated. Means its length will be changed. Suppose capital L is the original length of that wire and small l be the change in length, then strain is equal to small l by capital L, means change in dimension to the original dimension. That is given here. If a wire of length L increases by length small l, then the ratio small l by capital L is called strain. Means strain is equal to small l by capital L. As strain is the ratio of same quantity, so it get cancelled, hence strain has no unit, no dimensions. Means in other words, strain is dimensionless and unitless quantity. For example, if we consider length, then unit of length is centimeter in CGS unit. So centimeter get cancelled. So it has no unit and dimension. Then Hooke's law. Hooke's law is the fundamental law of elasticity and was expressed by Robert Hooke in the year 1679. He measured the strain produced in different materials by subjecting them to different values of stress. From these experiments, he established a relation between stress and strain, and this relation is called Hooke's law. The law can be stated as, this is a very simple statement, within the elastic limit, stress is directly proportional to strain, or provided the strain is small, stress is proportional to the strain. Hence, stress is proportional to strain, or stress upon strain is equal to constant. And this constant is called the modulus of elasticity or coefficient of elasticity, and is a property of the material of the body having unit as that of stress. Means unit of modulus of elasticity and unit of stress is same, because when we consider this relation stress upon strain is equal to constant, we know unit of stress in SI unit system is Newton per meter square and strain has no unit. So unit of stress and unit of coefficient of elasticity are same. Or modulus of elasticity is equal to stress upon strain. Means modulus of elasticity is defined as the ratio of stress to strain. Hooke's law obeys if deformation is small. If the body is stretched beyond the elastic limit, then stress is not proportional to the strain and Hooke's law is not obeyed. Means Hooke's law holds up to a maximum stress called the proportional limit. Then Young's modulus. Corresponding to the three types of strain, there are three moduli of elasticity. First one is Young's modulus, then bulk modulus and modulus of rigidity. Young's modulus is denoted by letter capital Y, bulk modulus is denoted by capital K, and modulus of rigidity is denoted by eta. So let us first consider Young's modulus, that is capital Y. When deforming force is applied to the body along a particular direction, the change in length per unit original length in that direction is called longitudinal or linear strain. And the force applied per unit area of cross section is called longitudinal or linear strain. And the ratio of longitudinal stress to linear strain within the elastic limit is called Young's modulus, which is denoted by capital Y, or in some other books it is also denoted by capital E. If L is length of wire, capital A is area of cross section, and force F is applied to a wire so that it can stretch and its change in length is small l, then Young's modulus is equal to longitudinal stress to the longitudinal strain. This is by definition. Putting values of longitudinal stress to the longitudinal strain here. We know value of longitudinal stress. Stress is nothing but force upon area, and strain is change in length to the original length. If F is force and A is area, then longitudinal stress is F upon A. And if small l is change in length and capital L is original length, then small l by capital L is longitudinal strain. So we get F upon A upon L upon L, or Y is equal to, that means Young's modulus is equal to F into capital L by A into small l. The unit of Young's modulus is dyne per centimeter square in CGS system and Newton per meter square in SI system. And the dimension of Young's modulus are same as dimensions of stress, means M1 L0 T minus 2. Only solids have Young's modulus. Liquids and gases do not have Young's modulus because they do not have a length. Then work done during longitudinal strain. Consider a wire whose one end is fixed to the rigid support and stretching a force F to the end of a wire. When a body is in its natural shape, it possesses a minimum potential energy. When external force is applied to a body, then body gets deformed and the molecules are displaced from their equilibrium positions. The intermolecular distances change and restoring force acts on the molecules so as to take them back to their original position. Means when the body is deformed, the work is done by external applied force against the internal restoring force. This work done is stored in the body in the form of potential energy. Hence, potential energy of the body is increased, and this is called elastic potential energy or energy of strain or simply strain energy. So, we can obtain the strain energy, means work done during longitudinal strain. For that, we have to consider a wire whose one end is fixed to the rigid support and a force F is applied to the other end as shown in figure. So this is a rigid support. Consider a wire whose one end is fixed to the rigid support and stretching force F is applied to the wire. This is a length, capital L is length of wire. Capital A be the area of cross section of wire. The force is applied by an amount F is equal to A into Y by L into X. X is the extension in the wire due to applying a force. So this is extension X. The wire is under a longitudinal stress, that is F upon A. This is a definition of stress, and the strain is change in length to the original length, that is X by L. Then Young's modulus is Y is equal to stress upon strain. The force is here, the force is so adjusted that the wire is only slowly stretched. Therefore, at any time during the extension, the external force equals the extension in the wire. Putting values of stress and strain, we know that stress is F upon A, where F is deforming force or applied force. Capital A be the area of cross section, X is extension, and capital L be the length of wire or original length. By rearranging this, we get capital F into capital L by capital A into X, or value of F is AY into X by L. The work done by the external force in a further extension dx is dW is equal to F dx. This is basic definition of work done, force into displacement. Putting value of F here from above equation, as we know that value of F is AY into X by L. So we get dW is equal to AYX by L into dx. The total work done by the external force in an extension from 0 to L will be W is equal to integration of dW from 0 to L. So putting value of dW here, W is equal to integration AYX by L into dx from 0 to L. As area A, Young's modulus Y, length L are constants, so we get an integration of x dx is x square by 2 from limit 0 to L. Therefore, we get W is equal to AY L square upon 2L. This work done is stored into the wire as elastic potential energy or strain energy. Thus, the elastic potential energy of the stretched wire is capital U is equal to AY into L square by 2L, or U is equal to 1/2 AY L by L into L. Means L square is separated here. This L square is separated here, or U is equal to 1/2 into stretching force into extension. In the relation of Young's modulus, we can calculate the value of force, that is AYL by L, which is stretching force, and this L is extension. Hence, work done per unit volume of a wire or strain energy per unit volume of a wire is elastic potential energy, that is U, divided by volume, and volume is area into length, so A into L. So we get U upon AL. Which is equal to, putting value of U here, that is 1/2 AY L by L into L. This is value of U, that is strain energy, into extension divided by volume of a wire, that is area into length, which is equal to 1/2, this 1/2 as it is, and value of AYL by L is force F, that is stretching force, into extension as it is by A into L. Again, by adjusting 1/2 as it is, we can write this F and A in one bracket and this small l by capital L in another bracket. So we get 1/2 F upon A into L upon A, L upon L. And we know value of F upon A, that is stress, means force upon area. And what is this? Change in length to the original length, means change in dimension to the original dimension, that is strain. So we get 1/2 as it is, F upon A. Instead of F upon A, we can write stress, and instead of small length by capital length, that is strain. So we get work done per unit volume of the wire or strain energy per unit volume of the wire is equal to 1/2 stress into strain. Thank you.